Perfect. Thank you for the introduction, Michael. I hope you're not too hyped after this introduction. So in any case, as you can see, my talk will be on a mechanism of baryogenesis for causal fermion systems. In the first place, we already discussed a bit of what is baryogenesis about, or about the baryon asymmetry in Myri's talk. But let me just very briefly, to set the stage, mention what I mean with baryogenesis. So I'm referring to matter creation process, particle creation process, which is to explain the observed matter asymmetry. Why do we need to explain such a phenomenon? Well, because the Dirac equation predicts particles and antiparticles to be created in pairs. Hence, it predicts a symmetry between matter and antimatter, which we do not observe. We observe a matter asymmetry, okay? For the physicists among you, whenever I use the word particle, I'm referring to fermions. I will stick to this. And yeah, so the aim or the goal of this talk is twofold. In the first place, I will acquaint you with the mechanism of baryogenesis, initially suggested by Felix and Claudio in the theory of causal fermion systems. And secondly, we will discuss some of the details on how to describe, model, quantify such a mechanism of baryogenesis. I will present you some results we've obtained for conformally flat spacetimes. Okay, so what are the main a prioris, the main assumptions which lie at the core of this mechanism? Well, in the first place, with respect to the dynamics of the spinors, as I mentioned before, the Dirac equation does not predict a matter asymmetry. Hence, we will assume that the spinors, the sections of the spinor bundle, evolve according to dynamics which deviates slightly from this Dirac dynamics, okay? Now, secondly, with respect to the regularity of space-time, instead of working with smooth manifolds, we assume that beneath minimum length, this regularization length, the manifold structure breaks down. What practical implications does this have? Yeah. We will still consider a smooth spacetime, but instead of working with smooth sections of the spinor bundle, we consider distributional ones, so spinors in a certain Sobolev space, say weak solutions to the Dirac equation. Then, of course, if we want to evaluate them pointwise, they might not even be continuous, so we need to regularize them, okay? Now, this leads us to the next main assumption, which is on what are the main physical objects, or what is the most important physical object that appears in this baryogenesis mechanism, and this is namely the regularization operator. So as I mentioned before, if we want to evaluate pointwise these distributional sections of the spinor bundle, we need, of course, to regularize them. These regularization operators are well known in spin geometry. Concrete examples are Friedrich modifier smoothing operators. But for us, they are much more than a technical tool. For us, they have the main physical significance, since it's these operators that bridge the gap between the possibly discrete nature at the very small scales in the quantum world and the smooth structures we have at the very large scales in general relativity. Okay, so furthermore, we can see these operators as being pointwise defined through space-time, and in this sense, we also have a dynamics for them. Now, more concretely, what implications? So this assumption, putting these regularization operators at the center of the mechanism I will present, what implication does this have? That instead of working with the distributional section of the spinor bundle, we will directly work with these regularization operators and with their dynamics. Now, let me briefly sketch what is the structure of this talk, since it might be very useful to see how these assumptions I mentioned before pop up, the role they play. So we will start, let's see if it works. Yeah, we will start constructing a particular type of regularization operators. We will define the dynamics for them. Then we will use this to define a spinor dynamics which deviates slightly from the Dirac dynamics. And then, of course, we will address the question of whether does this give rise to baryogenesis or not. And if it does, to how much? Can we quantify it? Okay, now before we enter the main concepts that appear here, let me address the question of how do we even want to mathematically model a process of matter creation. So let's start with the simplest example, Minkowski spacetime, where particles and antiparticles have a clear interpretation. They correspond to eigenstates of the Dirac Hamiltonian corresponding to positive, to negative, respectively negative eigenvalues, okay? And now, very roughly, what is the intuitive idea of how we want to model a matter creation process? How do we want to mathematically describe baryogenesis? So based on this picture, or on this idea of how, let's see, I think the battery, no. Yeah. I actually have a red light here, so at some point it might stop working, but well, in worst case, I continue afterwards with the keyboard. So what is the rough idea of how we want to describe baryogenesis mathematically? Well, we want to describe this as a relative change between spectral subspaces of an operator, which is to generalize the Dirac Hamiltonian to the concrete space-time we're interested in working with, okay? So as I say, now I'm being very vague, now I'm just giving a rough idea of what we want to do. In the next slides, we will implement this. Yeah.
You just stated in Minkowski space, the spectrum is absolutely continuous, it's correct, but that means it doesn't have any eigenvalues, so I don't understand what you mean by part.
Okay, yeah, sure, yeah. Yeah.
So you mean generalized eigenfunctions?
Yeah, exactly, yeah. That's a good point, yeah. Sure, it's an absolutely continuous, yeah, spectrum. So generalized eigenfunctions, yeah. And actually that the spectrum is absolutely continuous plays a very important role afterwards too. Now, before introducing the main concepts in order to describe baryogenesis, let me set the stage from the geometry side. We will exclusively focus on conformally flat spacetimes, where the conformal factor is given by this capital omega here. We choose a certain time function, and then we will work with the foliation given by its level sets, okay? Furthermore, we will fix Hilbert space given by these L2 sections, and then we will also fix a future directed time-like vector field, globally defined through space-time. This I will refer to as the regularizing vector field, and the idea is that this vector field is to describe the regularization dynamics. How it's constructed, I don't really have time in this talk. We can discuss afterwards if you want, but these are the main geometric concepts we'll need. And now we can see, Now we can move on to the main three concepts we will need in order to describe baryogenesis in this setup. So we start by introducing the operator, which is to generalize this Dirac Hamiltonian in Minkowski spacetime to a general conformally flat spacetime, which is this symmetrized Hamiltonian, okay? And as you can see, it basically contains simply three distinct objects: the regularizing vector field, the Dirac Hamiltonian, and the spin connection. And you can show that it is essentially self-adjoint, and from now onwards, we will denote its unique extension with the same symbol. Okay? Now, a couple of remarks regarding this operator. Since it's self-adjoint, it's easy to see that it's the associated spectral projection operator. It's a densely defined bounded operator, so it has a unique extension to the full Hilbert space. This we can, and so from now onwards, I will refer to this, I will simply work with this unique extension. And why do we want to extend it? Well, you can actually show that if your space-time has a bounded geometry, your interval is bounded, that this spectral projection operator is a regularization operator in the sense that it maps L2 sections to smooth sections, okay? And furthermore, its dynamics by construction is determined by how our vector field evolves through space-time. Okay, so now we have a regularization operator. We have a dynamics for this regularization operator. If you remember this schematic structure of the way we would proceed of the talk, the next step was to introduce a spin dynamic. Okay? And this we do through adiabatic projections. These are adiabatic projections involve two distinct objects, the spectral projection operator and the unitary Dirac evolution operator, okay? And this is this operator which is to describe a spinor dynamics which deviates from the Dirac dynamics. Now, once we have this, we can address the question of modeling a matter creation process, modeling baryogenesis. If you remember the intuitive idea, the rough idea was to describe it as a change, a relative change between spectral subspace. So this is implemented, let's see, this is implemented through this definition here. Of course, we have to guarantee that this operator product is trace class, and this is where this cutoff function eta plays a very important role. So when we actually need to compute things, we need this eta function because the Hilbert space is infinite dimensional. This in general, if we don't consider this eta functional, this cutoff function will not be trace class. And this, before I forget, this H tilde is nothing more than the operator which is unitarily equivalent to the Dirac Hamiltonian in Minkowski spacetime. Okay? Now, once we have the three main concepts in order to model, to describe baryogenesis, we want to see if baryogenesis takes place or not. And in particular, can we get concrete formulas out of that that might at some point lead, or that might lead to predictions. Okay, so the goal is to quantify this perturbatively through a perturbative expansion of this rate of baryogenesis for conformally flat spacetimes. And in order to do this perturbative expansion, we need three assumptions. We need, again, to assume that our conformally flat spacetime has a bounded geometry, that this symmetrized Hamiltonian has an absolutely continuous spectrum, and that in particular this symmetrized Hamiltonian splits in two parts. One of them, this operator, which is unitarily equivalent to the Dirac Hamiltonian Minkowski spacetime. A second part, which we can treat as a small perturbation, in which we need to assume to have smooth, compactly supposed coefficients. This is important in order to guarantee trace classness of the operator product appearing in the definition of the rate of baryogenesis. And secondly, we need an upper bound on how large this perturbation can be, is allowed to be. And this guarantees us actually convergence of the Neumann series when performing the perturbative expansion. Now, let me, as the perturbative analysis gets quite complicated, let me just mention qualitatively some of the results we get out of them. Well, the first one was already obtained by Claudio and Felix. That is basically that no baryogenesis takes place if the spinors follow the Dirac dynamics. Afterwards, we also saw that actually no baryogenesis happens if the mass of the fermions is set to 0, and if you assume that your regularizing vector field is equal to d by dt. Okay? Now, secondly, you might wonder what happens in Minkowski spacetime, which is when we do not expect baryogenesis to happen. And actually, we can see that no baryogenesis happens if you assume your regularizing vector field to be E and to agree with d by dt. Okay? But okay, what happens now in more general conformally flat spacetimes in FLRW and in all the interesting conformally flat spacetimes? Now we see that the 0 and first order vanish, whereas the second order has a relatively complicated form. It is in general non-zero. Yes.
So you got this is Euclidean, right? Because I mean, you say bound geometry.
Yeah, okay. I'm being very vague just to be quick, but we basically need to assume that on a certain, because we compute everything on a Cauchy hypersurface, we need to assume that outside of a compact set, it is Minkowski again. Our conformal factor goes to 1 if you want. So here I'm being very vague, but this is an assumption we need in order to perform this perturbative expansion. So in a certain sense, this rate of baryogenesis can be understood as a density of a rate of baryogenesis because we can only assume things to happen in a certain place, the geometry to be turned on in a compact region. So this is the idea, and this is something we need for computational purposes. Otherwise, I mean, in the previous things, well, except for proving that the spectral projection operator maps to the smooth sections. We didn't need it, but here we do. Okay, well, I mean, that we need it too, but apart from that, and the rest we don't. Okay, now, as I said, well, I'm close to the end, so this would be the general expression. It's quite complicated for the second order contribution. This and particular example, if U agrees with d by dt, then this scales as the mass squared. Okay, just to get an idea of how large this effect is for general conformally flat spacetimes. And now, just to finish, you might wonder, our whole construction from the very beginning depends on the choice of a time function, of a foliation. So how canonical is our construction? However, if you remember already from the beginning, also we need to choose a privileged future-directed time-like vector field or a privileged time-like direction. So one way out of this problem might be to simply choose the time function that minimizes the misalignment between d by dt and the vector field u. Here I'm being very vague. If you're interested in more details, we can discuss this after. This is work in progress using we have shown that such a time function exists and is unique in the case where we're working with spacetimes with compact Cauchy hypersurfaces. We expect the same to hold for asymptotically flat manifolds, but this is still work in progress. But as I say, in the compact Cauchy hypersurface setting, it exists, it's smooth, it's unique. So this is what I would like to finish with. Thank you for your attention. If there are any more questions, I'd be glad to answer them.